Hello, my name is Ryan Verghese, and in this video, I'll be presenting my project on optimizing privacy budget for multiple correlated queries. This work explores how we can move beyond naive composition methods to make differential privacy more practical for real-world applications. So let's start with like a scenario. So like imagine like a hospital that needs share statistics with medical researchers. They need to answer questions like what is the average age of our patients, and what is the average age of patients with heart disease. Researchers typically need 50 or more such statistics for meaningful analysis. Each answer must protect privacy protection, but here's a question: how do we maintain privacy while keeping this data useful? And this is the problem or questions for my project that it addresses. So to protect privacy, we add random noise to each answer. This is differential privacy. The traditional approach splits our privacy budget equally among all queries. So if we have 50 queries and a total privacy budget of epsilon equals 1, each query gets epsilon over 50. The problem is, with such small privacy budget per query, we need to add massive amounts of noise. An age that should be 47.2 years might be reported as anywhere from 32 to 62 years, and this data becomes essentially useless. So my research question is simple, but can we do better? Can smart algorithms reduce the noise while maintaining the same privacy be guaranteed? And my hypothesis is yes, by exploiting the structure of queries and using advanced composition techniques. And you will see here that we can achieve around 40 to 50% improvement, which makes a huge difference. So this is my technical formulation. We have a dataset D with n records. We need to answer k queries. This could be averages, counts, or other statistics. We have a total privacy budget epsilon total that we must respect for differential privacy. Our goal is to minimize the total error minus the sum of the differences between true answers and noisy answers. The traditional approach allocates epsilon over k to each query, which means error grows linearly with k. By the time you reach 50 or 100 queries, the system becomes unusable. This is the challenge that we are addressing. So why does naive approaches fail mathematically is that in basic composition, privacy losses add up linearly minus epsilon total equals the sum of all individual epsilons. So for like 50 queries, each query gets epsilon over 50. Since noise is inversely proportional to epsilon, we're adding 50 times more noise than if we answer a single query. But this give us some questions like, is the linear addition too conservative? Can we exploit the fact that many queries are correlated? And well, the answer is yes. I use four approaches to this. First is naive Laplace, which is our baseline that splits epsilon equally. Second is advanced composition that uses square root of k, scaling instead of k. And third, the sparse vector technique that only pays privacy costs when needed. And the last one is histogram release that pays a one-time cost to answer unlimited queries. So advanced composition is based on a tighter mathematical analysis. So instead of each query getting epsilon over k, they get epsilon over square root of k, which seems like a small change, but it's very huge. So for example, like 50 queries, naive gives each query epsilon over 50, while advanced composition gives epsilon over 7. That's literally 7 times less noise. We also use Gaussian noise instead of Laplace because it has a better composition properties. And the result is, well, 45% less error with the same privacy. Sparse vector technique is good, which you can think of it like it's like a toll road where you only pay when you exit. We're answering threshold queries like is the average age above 40? If the answer is no, we answer for free, so no privacy costs, and we only pay when the answer is yes. So this means we can answer over 100 threshold queries compared to just 10 with a naive method. So this is like good for monitoring system that check if metrics exceed certain thresholds. For histogram release method, I use a strategy is that we release a noisy histogram of ages once using our entire privacy budget. Then we can answer unlimited queries from this histogram with no additional privacy costs. The trade-off is that each individual query is less accurate since we're working from bin data. But for applications like public dashboards that need answers of 100 queries, this is good. So I tested this on the UCI adult dataset with over 32,000 records. And with 20 queries, advanced composition reduces error by 45%. With 50 queries, it's 48%. And it keeps getting better as we keep adding more queries. For threshold queries, SVT answered over 100 queries while naive method uses all their budget at just 10. These aren't just like marginal improvements, they make the difference between usable and unusable systems. So when should you use each of these methods? Well, for fewer than 10 queries, just use naive. Its simplicity wins. It's basic good. For 10 to 100 queries, use advanced composition. So if you're asking threshold questions, use SVT. And if you need unlimited queries, like a public dashboard, use histogram release. So here's an example. A daily report with 5 statistics, use naive. A researcher that studies with 50 queries, use advanced composition. And a monitoring system checking thresholds, use SVT. So why does this matter? Well, these techniques are good used in practice. The US Census use advanced composition for release and statistics. Google and Apple use these methods for privacy-preserving analytics. And the healthcare organization use them for HIPAA compliant reporting. The smart algorithm makes privacy affordable, and 40 to 50% improvement equals privacy becomes practical. So to summarize this, smart algorithms achieve 40 to 50% noise reduction over naive methods. Different techniques are optimal for different scenarios. And most importantly, these improvements make differential privacy practical for real-world employment. Future work could explore adaptive mechanisms that automatically select the best technique based on the query work overload. Thank you.